Okay. All right. So today we're gonna continue where we left off yesterday or Monday. But I just want to go over a few things. Remember that when we see y to the 7th, right? This is the base. That's the exponent. It means how many times we've multiplied that base by itself. So y to the 7th means y times y times y times y times y 7 times, right? Okay? And then sometimes you might see a power taken to a power. So this means x to the 3rd, which is x times x times x, to the 2nd. So that times itself twice. Okay? And then I think the last one I want to talk about was with the subtraction. So remember we spent a little time talking about the properties of 1. We know that when you divide a number by itself, so x divided by x, you get a 1. So we're left with x times x, which is just x squared. We're actually left with 1 times x, but we just write that as x squared. Okay? So don't forget when we're figuring this out, some of you already got to the point where you're like, oh, I did that in my head, I got it. That's absolutely fine, and you can do that. But if you're not yet, we know what to do. We know that x to the 5th is just x times itself 5 times. Divided by x squared is x times itself twice. We go back through and we use our properties of 1. We know that anything divided by itself is 1. Anything divided by itself is 1. And we're left with x times x, which is x to the 3rd. So if you're having a hard time with the more difficult ones like this guy, think back to the basics and remember that you can always write it all out and think about it that way. So if you ever get stuck with something more difficult, think back to those easier problems that you started with. Okay, so regardless of where you left off on Monday, I'd like to see everyone starting here with these problems A through L. And I would like to see you working with your group, as these are the ones I'm talking about, like these harder ones that seem more complicated. Think back to the earlier problems. Yeah. If you're done with this, then I'll talk to you guys about something else. So I'm going to predict about 20 minutes to work on this. And here, let me be, just write it up in here. Yeah. Or hold on. Okay.
Okay, so.
Talk it out.
So this is x and
Talk
x.
to your audience.
So this is x times x. That's like 3 times, so I just times these two together and it'll be x to the 6th power. Wait, and then you do y, and then 3 times y.
Not 3 times y times
Or
itself 3
y.
times.
Yeah.
Okay, so thank you. Let's say that you were not quite on the same page as Bruno yet. You could write it all out. We know that this x squared is x times x over y. And I'm going to write this 3 times x times x over y. So that's x times itself 6 times and y times itself 3 times. So if you're not quite to this point, write it all out. But please make sure that you remember that this to the 3rd power applies to this and to this. So don't forget that. Okay, some other ones that seem to be tricking people that I saw was this 5h times 2h to the 24th. Anyone want to do that one? Abby, you want to do it?
Okay, so first of all, like h is equivalent to h to the power of 1.
Okay, why?
Because it's just like h. It's not timed by anything. It's just there's like 1h there, so it's h. To the
So
power of
Riley,
1.
did you catch what Abby just said? When h has no exponent by it, what's its power? 1. Great, so just like x squared is x times x, that's x to the 1 times x to the 1. So x by itself with no power is just 1. So she's telling us that h to the 1st, okay?
And this is 5 times h power of 1. And 2h times 2 times h to the power 24. It's actually like 2H 24. So, which is easier to like multiply. So it's like, except the 5 and the 2 are separate from the H's. So all you need to do is like rearrange like the multiplication. So it's like 5 times 2 times H to the power 1 times H to the power 24. And here it's kind of easy, we can just do 10. But here, if you can just do like H times H 24, which is, you can like turn that into like 24 H's and so on. And then you multiply that by 1 H, you get H power 25. So multiply these together, you get 10 H 25.
Thank you very much. So, guys, Abby brings up two good points. The first one is when you see an expression like 3xy squared, that means it's 3 times x times y squared. Let's remember that, okay? That's why you can remember that the squared only goes to the y, because it's separate. Order of operations is you do exponents before you multiply. So you can remember that you can separate that out. And then she referred to moving them around. So if this is times 3, I can rearrange that commutative property of multiplication, and I can say 3 times x times y to the second. And maybe that's easier for me to visualize how that becomes 9xy squared. Okay, she also brought up another good point. She said h times h to the 24th. If you're not sold on this being a 1, here's another way of looking at it. H to the 24th means I'm multiplying h by itself 24 times. And then I'm also multiplying it by another h. So if I've got h times h to the 24th, clearly I've multiplied by itself 25 times. So that would also indicate to us that that's a 1. Okay, so there's a few more things I wanted to talk about. This one, not how many h's there are, it's how many times h is multiplied by itself.
But like how many, yeah.
Yeah.
And what point, and like we're just H, it's just H.
Yeah, just itself, not multiplied by itself at all. Okay, so this one I also saw tricking people a little bit. So let's remember what Abby said. We're going to break it up. We've got 3 times k to the 20th. And this entire thing, we're multiplying by itself 4 times. This should help us out a little bit. So I'm taking this whole thing, and I'm saying I'm going to multiply by itself twice, 3 times, 4 times. So what is 3 times 3 times 3 times 3? Riley?
3 times 3 is 9, right?
Yep, times 3
27.
times 3.
I'm not sure. 1 second.
Call it out if you know.
81.
81. So that 3 times 3 times 3 times 3, which is 3 to the 4th. And then I've got k times itself 20 times, 20 times, 20 times, and 20 times for a total of 80k. Or k to the 80th is what I mean.
If you like need help of like multiplying like exponents of like numbers, all you need to do if you get like something like 3 to the power 4.
So I'm going to pause you right there because we're going to get there next. You're jumping the gun a little bit. Okay, I think those were the only ones I wanted to touch on. Is there anyone that you really want to go over right now? Oh, you know what? There's one more. This one here, we have 24 hg squared over 3h to the 9th. So if we wrote this out, because I saw a lot of people that got this slightly incorrect, so please pay attention. 4, 5, 6, 7, 8, 9. This one's worth writing out because it's a little different than all the other ones. The 24 and the 3, we can simplify that to make 8. H divided by h is just 1. G divided by g is 1. G divided by g is 1. So what do I have up top? 8 times 1 times 1 times 1, which is 8. And what do I have on the bottom? I've got g times g times g times g, 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 which is what?
G to the 7.
Okay. But notice that it's g to the 7th power in the denominator. So I can't just make this 8g to the 7th, even though I might want to, because I need to recognize that those g's are all on the bottom. Right? And being on the bottom means you divide by those, so it would be like turning 1/2 and just saying, oh, that's 2. It's not. So you gotta make sure you account for the fact that they're on the bottom. So you guys over there, I think, have this incorrect. So make sure you fix that on your page. All right, so what I would like to do right now is give every... All right, guys, I've seen people are having the same difficulty with this, so I just want to explain it real quick. So most people, I think everyone was able to get here. The answer is m to the 10. But what I want is, how do you tell someone how to do this if they're not looking at this specific problem? So one example is if a letter or number is the same, sorry Adrian, I did the wrong one. If a letter or number is the same, you just add the exponents in a multiplication problem. So this is a generalization for how we do this problem. If the letter's the same, add the exponents in a multiplication problem. This is a good generalization for that problem. So we're going to try and do the same style, but for the second two problems, okay? What? So we're going to go back to this. You can explain it the second time. I want you guys to keep working, and then we'll come back. And then I'll write it down. So the expression is x to the 20th times x to the 40th. That would be x to the 65th. The generalization, so for x to any power times x to any power, n, or n, I'm going to get x to the m plus n. So that's just a way of explaining it for any given situation. X to any power times x to any other power would be x to those powers added together. So that's the reason why it looks like that with the m and the n. Don't get confused.
So just saying it, add those two numbers together.
It's just saying, yeah, x to any power times x to any other power, you add those two together. Okay? And then you're going to write down some sort of generalization. So I liked in a multiplication, when you're multiplying expressions, or let's say when you're multiplying terms and the variables are the same, you can add the exponents. So that's what I'm going to write down. So I'm going to say when multiplying terms, with the same variable, you can add exponents. So you are welcome to write down whatever generalization made sense to you from the ones that we talked about. Okay. So I think I'm actually going to skip looking at the explanations for this because I think what I did was make it a little too complicated. The problem that I gave you guys was 10. Can someone read it to me?
It's
10 times x squared times y.
Okay, then it was 2x, y, z to the 7th.
Yeah.
Right? So the problem with this is I kind of asked you to do too much, so you didn't get down to the simplest kind of generalization that I was looking for. Some of the things that you guys wrote about. What were some of the generalizations? So I think you guys said over there, Cheyenne, what do I do when I have whole numbers like this? Yeah, so I would divide 2 and 10 to get 5. And then you have this, what do I do when I have y divided by y?
whenever you have two of the same number.
When it's the same thing on the top and the bottom, that's y divided by y, which makes 1. So it cancels out and becomes 1. What I really wanted to get at, though, what I really wanted to get at, though, is what do I do when I've got a problem like this? Riley.
When the variables are the same, you can subtract the exponents.
When the variables are the same, the bases are the same, and I'm dividing, I can just subtract the exponents. So I would get 30 minus 15, x to the 15. Okay? And the reason that I can do that, everyone kind of figured this out, I think. Like w to the 5th over w squared, when you write out all those w's, you could see how many you were going to cancel out. And then it occurred to you that that's a subtraction problem. So when we get bigger numbers, it just makes more sense to sometimes subtract rather than write it all out. So if we go back to the camera, all right, and let's look at our last one. So the last one that we looked at was x to the 5th over y to the 2nd. So when you're taking an exponent to a power, so an exponent to a power, what is a general way of expressing what happens to the solution? General way, or no?
I said whenever you power an exponent, then you can just times the.
Okay, so when I take a power to a power,
Yeah.
I multiply the exponents. So it would be x to the 5 times 2 over y, and since that's power of 1, it would be 1 times 2. So I've got so my answer would be x to the 10th over y to the 2nd. So Adrian, how did you want to explain it?
No, that's not
Same thing?
good. Yeah, that's
Okay, so when I have a power taken to a power, the general way that I can explain that to someone, Victoria, what would I do?
So you take a power to a power, then you multiply the exponent. And you take a power to power, multiply it by the exponent.
Yeah, so when I take a power to a power, multiply those exponents. So x to the 3 times 100. Okay, so I have m to the n, so that would be x to the m n. So the m times n. X to the m times n. Over here would be x to the 5 times 12, which is 60. So I'm going to write that down. I think Victoria said, well, when you take a power to a power, multiply the exponents. So when taking a power to a power, multiply exponents. Hold up your answers, please. Hold them up. Alright, check yours again. Alright, can I get a volunteer to show us up here? John, you want to do it? Okay, tell me what you got. What are the like terms that I can box? Okay, so I've got 12R and 3R. And you know what, actually, something that I want you guys to make sure you do, and I don't see it on everyone's, is this 3R, it's a positive 3R. So we're going to box that plus 3 as well. Okay, so not just the 3R, but the positive 3R. Okay, now what? What else?
So 12R plus 3R is 15R.
Okay, 12R plus 3R is 15R. Okay, what else are my like terms?
Plus 5.
I've got a positive 5, good job. And?
It equals 20 and then minus 5.
Oh, hold on. So I have plus 5 is a like term with what?
Minus 5?
Yeah, the negative 5. So I can't add that 5 to the 15. What I can do is I can add positive 5 and negative 5 and I get 0. So my answer is 15R. Okay? So you can't add that 5 to the 15R. Okay. All right, erase your whiteboards. I got 2 more problems for you. Will you talk to us what you're doing?
So x2 and dx2 are like terms.
So hold on one second. Think back to the last problem that we did. It's not just 3x to the second, it's...
Dx to the second power.
No, I know, but it's not just that. Is it positive or is it negative?
Positive.
Okay, so can you add in the plus sign to that square?
And so since 2x and 2 are like terms, we don't combine them. But x2 plus, or x to the second power plus 3x to the second power is 4x to the second power plus 2x.
Right, great. So that's as far as we can go. That might not feel very settled since you have 4x squared plus 2x and 2, but that's as far as you can go as far as adding it down. So I also want to make sure. Can you box the terms for us first? Okay, so he sees that 2xy and a positive 3xy are like terms. Positive 2 and positive 4 are also like terms. Yeah. So 2xy and 3xy add up to 5xy. 2 and 4 add up to 6. Then you're left with x. Good. So that's as far as you can go. 5xy plus 6 plus x. Okay, great. All right, so the first numbers that we have in the real number system are counting numbers. Nicholas told us that that was, what did you give us as an example? 1, 2, 3, 4, etc. Let's do a different color. 1, 2, 3, 4, etc. So what comes after that? What's the next number that you learn or the next idea? Counting numbers, kindergarten. You learn on your hands. 1, 2, 3. Then you add in a 0 for whole numbers. As you got larger, you added in negative numbers. As we got even larger, our math knowledge expanded. We learned rational numbers. So rational numbers are two things. They're anything that can be written as a fraction, and it's also a repeating decimal can be written as a fraction. So you might see numbers like 1.6666 repeating. That bar means repeating. So if it's written as a repeating decimal, that means it can be written as a fraction, so it's rational. So you might want to add this note. Can be written as a fraction. And then to separate out the irrational, there are ones that can't be written as a fraction. And real numbers are all these things that we're talking about. And if you want, like on the outside of the real numbers, you can write imaginary, if that helps you remember that they exist.